Welcome to my Sleep Science channel. Before we begin tonight's journey, please take a moment to like the video, subscribe to the channel, and tell me where in the world you are listening from. Whether you are resting beneath city lights, surrounded by quiet countryside fields, or listening during a late-night drive, I'm glad you are here. Tonight we explore one of the most fascinating questions imaginable. What is the loudest thing in the universe? At first, the question seems simple. Everyone understands loud sounds. A barking dog, a passing train, a thunderstorm rolling across the horizon. These sounds fill the air around us and reach our ears through invisible waves moving through the atmosphere. Yet when we lift our eyes toward the stars, the answer becomes much more mysterious. Most people have heard the phrase that space is silent. In many ways, this is true. If you could somehow stand safely between Earth and the moon, you would hear absolutely nothing. No wind, no birds, no distant traffic, no whispering leaves. The emptiness between worlds contains almost no air, and without air, there is no familiar sound. This creates an interesting problem. If space is silent, how can there be anything loud in the universe at all? To answer that question, we first need to understand what loudness really means. On Earth, sound is a vibration traveling through matter. When a guitar string vibrates, it pushes nearby air molecules. Those molecules push neighboring molecules, creating a wave that travels outward until it reaches our ears. The louder the sound, the more energy is carried by that wave. The important detail is that sound requires a medium. Air can carry sound. Water can carry sound. Solid materials can carry sound. Empty space cannot. This means that many of the most energetic events in the universe produce enormous disturbances, but those disturbances often travel in forms very different from the sounds we experience every day. Imagine a volcanic eruption so powerful that mountains collapse and shockwaves circle a planet. Imagine a star exploding with more energy than billions of suns. Imagine two black holes larger than entire solar systems colliding at nearly the speed of light. These events release unimaginable amounts of energy. If they happened inside an atmosphere thick enough to transmit sound, the resulting noise would be beyond anything human ears could survive. When astronomers discuss the loudest events in the universe, they often mean the most powerful pressure waves, shock waves, vibrations, or energy releases. Some of these occur inside stars. Others travel through enormous clouds of gas between galaxies. Few are so immense that they distort space itself. The story becomes even more interesting because the universe is not completely empty. Between stars, there are tiny amounts of gas. Between galaxies, there are vast regions filled with extremely thin plasma. Although these environments are far thinner than Earth's atmosphere, they can still carry certain kinds of waves. The process is incredibly slow, but it allows astronomers to think about sound on scales far larger than planets. One famous example comes from a giant cluster of galaxies located hundreds of millions of light years away. Astronomers discovered enormous pressure waves moving through hot gas filling the cluster. The frequency was so low that a single wave cycle took millions of years to complete. If a human could somehow hear it, the note would be far below the range of hearing, deeper than any musical instrument could ever produce. As we travel through this series, we will encounter sounds that are not truly sounds. Sounds that humans can never hear naturally. Sounds hidden inside magnetic fields, and sounds reconstructed by scientific instruments. We will move from thunderstorms on distant planets to exploding stars, from pulsars spinning in darkness to black holes shaking the fabric of the cosmos. Along the way, we will discover that the universe may be silent in the ordinary sense, yet it is constantly vibrating with activity. Everywhere we look, matter moves, gas flows, stars pulse, galaxies collide. Space itself ripples and stretches. The deeper we explore, the more we find that silence is not the absence of activity. It is simply the absence of ears capable of hearing what is already there. And so, our journey begins with a simple realization. The loudest thing in the universe may not be a sound in the traditional sense at all. It may be an event so energetic, so vast, and so powerful that human language struggles to describe it. Understanding that possibility requires us to rethink what hearing means, what sound means, and what it means for a universe to be alive with motion while appearing completely silent. Far above our sleeping world, beyond the clouds, beyond the planets, beyond even the nearest stars, an endless symphony is already playing. The instruments are galaxies, black holes, magnetic fields, and ancient waves left behind from the earliest moments of cosmic history. Their music unfolds across distances so large that light itself needs millions of years to travel between notes. Yet, every moment, whether we notice it or not, that cosmic performance continues. When most people imagine outer space, they picture a place of complete silence, a lone astronaut floating above Earth, a distant spacecraft drifting between planets, endless darkness stretching in every direction. No wind, no voices, no movement, just perfect stillness. This image is surprisingly accurate, yet it also hides a deeper truth. Space appears silent, not because nothing is happening, but because the universe follows rules that are very different from those we experience on Earth. To understand the loudest things in the universe, we must first understand why silence dominates so much of space. Every sound you have ever heard has traveled through matter. The sound of rain striking a window, the rustling of leaves in a forest, the hum of an air conditioner, even the gentle sound of your own breathing. In every case, vibrations move through a material medium before reaching your ears. Air is the medium we depend on most. The atmosphere surrounding Earth contains countless trillions of tiny molecules. When something vibrates, these molecules pass the disturbance from one to another, like an enormous chain reaction. The process happens incredibly quickly, creating what we recognize as sound. Space is different. The distance between particles in interplanetary space is enormous. In many regions, a single cubic centimeter may contain only a few atoms. Imagine taking all the air from a room and removing almost every molecule until only a handful remain. That would still be denser than some regions of outer space. Because there are so few particles available to pass vibrations along, ordinary sound waves cannot travel efficiently. A massive explosion occurring millions of kilometers away would produce no audible noise for an observer floating nearby. The light would arrive, radiation would arrive, particles might arrive, but sound, as we normally understand it, would not. This fact often surprises people because movies frequently portray giant explosions in space accompanied by dramatic roaring effects. Real space would be much quieter. A spacecraft observing a distant star explode would witness a brilliant flash expanding across darkness without hearing anything at all. Yet complete silence is not the entire story. Although most of space is extraordinarily empty, it is not perfectly empty. Small amounts of gas exist between stars. Larger amounts of plasma exist in certain regions around galaxies and galaxy clusters. Plasma is a state of matter in which atoms have been stripped of some of their electrons, creating an electrically charged mixture that behaves differently from ordinary gases. The universe contains enormous oceans of plasma. The sun itself is mostly plasma. Many nebulae are composed of plasma. Vast regions between galaxies contain extremely thin plasma spread across unimaginable distances. These environments allow certain types of waves to travel through them, though often at speeds and frequencies very different from sounds on Earth. If humans possessed ears capable of detecting these cosmic vibrations directly, the universe might seem far less silent than we imagine. Consider our own sun. The surface of the sun constantly rises and falls in gigantic waves. Hot material moves upward from deep inside the star before cooling and sinking again. The entire solar body vibrates continuously. These vibrations create pressure waves that travel throughout the sun's interior. Scientists study these waves through a field known as helioseismology. By observing subtle movements on the solar surface, researchers can investigate structures hidden deep inside the star, much like geologists use earthquake waves to study Earth's interior. In a sense, the sun rings like an enormous bell. The notes are far too low and far too complex for direct human hearing, yet they exist. Beneath the brilliant sunlight lies a world of constant vibration. Many other stars behave similarly. Some stars pulse rhythmically, expanding and contracting over regular intervals. Others oscillate in dozens or even hundreds of different modes simultaneously. Entire stellar surfaces rise and fall in patterns that can reveal details about age, composition, temperature, and internal structure. The night sky appears peaceful, but countless stars are continuously vibrating. Silence becomes even stranger when we examine planets. Several planets in our solar system produce radio emissions generated by interactions between magnetic fields and charged particles. These emissions are not sounds in the traditional sense. They are electromagnetic waves. However, scientists can convert them into audio frequencies, allowing us to listen to representations of planetary activity. When transformed into sound, some planets produce eerie whistles, chirps, crackles, and haunting tones. The resulting recordings often feel less like natural sounds and more like messages from an unfamiliar world. Jupiter, for example, possesses an immense magnetic field. Charged particles trapped within this field generate complex electromagnetic activity that can be translated into audible frequencies. The result resembles a strange cosmic orchestra performing in darkness. These sounds remind us that hearing is often a matter of interpretation. Human ears detect only a tiny portion of the vibrations that exist around us. Many cosmic phenomena occur at frequencies far above or below our natural range. By converting them into audible forms, scientists reveal hidden layers of activity that would otherwise remain inaccessible. The concept of silence becomes even more complicated when we consider the scale of the universe. On Earth, sounds travel relatively quickly. A thunderclap reaches you seconds after a lightning strike. A passing vehicle can be heard from hundreds of meters away. Everyday distances are small enough that sound remains practical. Cosmic distances change everything. Suppose a pressure wave could travel through a giant cloud of gas between galaxies. The wave might require millions of years to cross the region. A single oscillation could last longer than human civilization has existed. Such a phenomenon would technically qualify as sound, yet it would bear little resemblance to anything our ears could recognize. The deeper astronomers investigate the cosmos, the more they discover that silence and sound are not opposites. Instead, they are parts of a spectrum shaped by matter, energy, distance, and perception. What appears silent from one perspective may be filled with vibrations from another. What seems empty may contain subtle waves traveling through thin plasma. What feels still may be undergoing motions so slow that entire civilizations rise and fall before a single cycle completes. As night settles over our small planet, the stars above continue their hidden motions. Giant clouds drift through interstellar space. Magnetic fields twist around planets. Stellar interiors pulse with immense energy. Invisible waves move through regions so vast that human minds struggle to imagine their scale. The universe does not sit quietly in darkness. Rather, it performs a kind of music that rarely reaches human ears. Its rhythms unfold over centuries, millennia, and millions of years. Its instruments are stars, planets, magnetic fields, and clouds of glowing plasma. Its notes are written across distances measured not in kilometers, but in light years. And within that immense cosmic silence, The first hints of truly extraordinary sounds begin to emerge. Long before stars illuminated the darkness, before planets formed, before galaxies stretched across the cosmos, the universe was a very different place. It was hotter, denser, brighter, and far more chaotic than anything we can observe today. If a traveler could somehow journey back to those ancient moments, they would not find the silent emptiness of modern space. Instead, they would encounter something that resembled a vast cosmic ocean, filled with motion, pressure, and vibrations. In a surprising sense, the early universe may have been the closest thing to a truly audible universe that ever existed. To understand why, imagine the universe shortly after its birth. Temperatures were so extreme that ordinary atoms could not exist. Matter and energy were packed together in an intensely hot plasma. Electrons moved freely instead of orbiting atomic nuclei. Light itself struggled to travel freely because it constantly collided with charged particles. The entire universe was not made of stars scattered through darkness. It was more like a glowing, turbulent sea extending in every direction. In this environment, pressure waves could move through the cosmic plasma. These pressure waves were remarkably similar to sound waves traveling through air. Regions that became slightly denser than their surroundings compressed the plasma around them. The compression spread outward. Neighboring regions responded. Waves traveled through the young universe, much like ripples spreading across the surface of a pond. For hundreds of thousands of years, the cosmos was filled with these enormous vibrations. If human ears could somehow survive inside that environment, they would not hear individual sounds like thunderclaps or explosions. Instead, they might experience a vast, continuous roar. Every region of space would contribute to an immense background, hum generated by countless overlapping pressure waves moving through the hot plasma. The universe itself was vibrating. This idea may seem strange because we often think of sound as something local. A door closes, a dog barks, a bell rings. In the early universe, however, the entire observable cosmos participated in a single interconnected system of waves. Some waves stretched across distances larger than entire modern galaxies. Others extended even farther. These vibrations carried information about the distribution of matter throughout the young universe. Tiny fluctuations in density created pressure differences. Pressure differences generated waves. Over time, those waves influenced where matter accumulated. In a very real sense, the large-scale structure of today's universe was shaped by these ancient cosmic vibrations. Modern astronomers can still detect evidence of them. One of the most important discoveries in cosmology came from observing the faint afterglow of the early universe, known as the cosmic microwave background. This ancient light has traveled across space for more than 13 billion years. Embedded within it are subtle patterns that reveal the influence of those primordial pressure waves. The patterns are extraordinarily delicate. Tiny variations in temperature, often smaller than a fraction of a degree, preserve information about events that occurred when the universe was still very young. By studying these variations, scientists can reconstruct aspects of the cosmic vibrations that once filled space. It is almost like hearing an echo from the dawn of time. Of course, these vibrations occurred at frequencies vastly different from sounds humans normally hear. The scale was enormous. Waves could take thousands or even hundreds of thousands of years to complete a single cycle. If converted into audio frequencies, however, researchers can create representations that allow us to imagine what those ancient oscillations might have sounded like. The results are haunting. Instead of sharp noises or sudden bursts, the reconstructed sounds resemble deep, evolving tones. They rise and fall slowly, carrying an almost musical quality. Listening to them feels less like hearing an event and more like experiencing the breathing of a living cosmos. What makes these ancient sounds especially fascinating is their connection to everything that exists today. The stars above your home, the planet beneath your feet, the atoms within your body. All of them ultimately emerged from a universe that once vibrated with immense pressure waves. Those waves helped shape where matter gathered. Regions slightly denser than average attracted additional material through gravity. Over billions of years, these concentrations grew into galaxies, clusters of galaxies, and vast cosmic structures stretching across hundreds of millions of light years. The universe we inhabit today still carries the imprint of its earliest vibrations. When astronomers map the large-scale distribution of galaxies, they find subtle patterns left behind by these ancient waves. The distances between certain structures reveal echoes of processes that occurred billions of years ago. The cosmic hum never truly disappeared. Its influence remains written across the universe. As the cosmos expanded, conditions gradually changed. Temperatures fell. Electrons combined with atomic nuclei. Neutral atoms formed. Light finally gained the freedom to travel long distances without constant collisions. This period transformed the universe dramatically. The dense plasma sea faded away. The environment that had supported enormous pressure waves vanished. The great cosmic roar slowly quieted. Silence, at least in the familiar sense, began to spread. Yet, traces of that earlier era survived. The ancient vibrations left fingerprints that astronomers continue to study today. Every measurement of the cosmic microwave background reveals another detail about those long-lost oscillations. Every map of galaxies provides clues about how primordial sound shaped the evolution of cosmic structure. There is something deeply comforting about this realization. The universe began not as a collection of isolated objects, but as a connected whole. Waves moved through it. Energy flowed across it. Every region influenced every other region. Long before stars shone in the darkness, the cosmos already possessed rhythms and patterns. In a way, the first great soundscape of the universe existed before the first sunrise, before planets, before oceans, before life, before anything that could listen. The cosmos was already humming. Those ancient vibrations are among the oldest traces of history that science can investigate. They come from an era so distant that ordinary human experience offers no comparison. Yet, they remain measurable, preserving a connection between our present world and the earliest chapters of existence. As the universe cooled and evolved, new kinds of sounds and vibrations would emerge. Stars would form. Galaxies would grow. Massive objects would begin shaping their surroundings through gravity and magnetic fields. Entirely new cosmic instruments would join the universal orchestra. But beneath all of them lies the memory of that first immense hum. The ancient resonance of a young universe, filled not with silence, but with waves moving through a glowing ocean of primordial plasma. Before we travel farther into the universe in search of the loudest phenomena ever discovered, it is worth spending a little time on the only world where humans have naturally experienced sound. Earth may seem ordinary when compared to exploding stars and supermassive black holes, yet it provides the foundation for everything we understand about loudness. Every sound that has ever reached human ears has done so because our planet possesses something surprisingly special. A thick atmosphere capable of carrying vibrations across great distances. Without this blanket of air surrounding our world, life would unfold in complete silence. The songs of birds, the crashing of waves, the rustling of forests, and even the sound of our own voices would simply not exist. Earth is not merely a place where sound happens. It is a world uniquely designed to make sound a constant part of daily experience. The atmosphere surrounding our planet acts like an invisible ocean. Although we rarely think about it, every breath we take comes from a vast sea of gas, extending hundreds of kilometers above the surface. When an object moves, vibrates, or collides with something else, it disturbs this ocean of air. Molecules bump into neighboring molecules, passing energy outward in expanding waves. Those waves eventually reach our ears. Where tiny structures translate them into electrical signals that the brain interprets as sound. This process occurs so naturally that it feels effortless, yet it depends on an extraordinary chain of physical events happening every second around us. Some of the loudest natural sounds on Earth come from thunderstorms. A lightning bolt can heat the surrounding air to temperatures several times hotter than the surface of the sun for a brief instant. The air expands violently, creating a shock wave that travels outward as thunder. When standing near a powerful strike, the resulting sound can be overwhelming. Windows may rattle, buildings may vibrate. The sound can seem to fill the entire sky. Yet even this dramatic event is tiny compared to many cosmic phenomena we will encounter later. Thunder feels immense because it occurs close to us, and because our atmosphere carries the energy efficiently. Volcanoes provide another reminder of Earth's ability to generate extraordinary sounds. During major eruptions, enormous amounts of energy are released in relatively short periods of time. Ash, rock, gas, and steam blast into the atmosphere with tremendous force. Some eruptions have been heard thousands of kilometers away. Historical records describe volcanic explosions that sounded like distant cannon fire across entire regions. In a few cases, people reportedly believed wars had begun because the sounds were so widespread and unexpected. The atmosphere carried those vibrations across distances that seem astonishing even today. The oceans contribute their own form of planetary music. Waves constantly collide with coastlines, generating a steady rhythm that has accompanied life for millions of years. Deep beneath the surface, shifting tectonic plates create earthquakes that send vibrations through both rock and water. Some underwater sounds travel astonishing distances because water conducts sound more efficiently than air. Whales take advantage of this property, producing calls that can cross entire ocean basins under favorable conditions. A single vocalization may travel farther than any sound humans could produce without technology. Human civilization has added countless new sounds to the natural environment. Cities hum with engines, machinery, electrical systems, transportation networks, and millions of daily activities occurring simultaneously. Even in a quiet room, subtle vibrations surround us. Air conditioning systems whisper in the background. Electrical devices emit faint tones. Distant traffic creates a constant low-frequency murmur. Complete silence is remarkably difficult to find on Earth because our atmosphere faithfully carries nearly every vibration that occurs around us. Interestingly, astronauts often describe one of the strangest aspects of space travel as the absence of familiar environmental sounds. On Earth, sound constantly provides information about our surroundings. We hear approaching weather, nearby movement, flowing water, and countless other signals. Remove the atmosphere, and much of that sensory experience disappears. Spacecraft interiors remain noisy because air exists inside them, but beyond the walls lies a realm fundamentally different from our everyday experience. The transition highlights how deeply connected human perception is to Earth's atmosphere. The loudest sounds ever recorded on Earth remain impressive achievements of natural power. Massive volcanic eruptions, giant meteor impacts, and nuclear detonations have all produced extraordinary shockwaves. Yet as immense as these events seem, they occur on a relatively small planet orbiting an average star. The universe contains objects far larger, energies far greater, and processes operating on scales that make even Earth's most dramatic events appear modest by comparison. Understanding our planet's sounds provides a useful reference point because it gives us something familiar against which cosmic phenomena can be measured. As night settles across continents and oceans, Earth continues its endless symphony. Wind moves through forests. Waves roll toward distant shores. Rain falls upon rooftops. Thunder echoes through storm clouds. Deep underground, tectonic plates slowly shift beneath mountains and valleys. Every one of these sounds depends upon the unique conditions of our world. They remind us that hearing itself is a privilege granted by the environment in which we evolved. Only after appreciating the sounds of home can we truly begin to understand how extraordinary the sounds of the wider universe may be. Every morning, the sun rises above the horizon with such familiarity that it is easy to forget what an extraordinary object it truly is. From Earth, it appears calm and steady, a bright disk crossing the sky with predictable precision. Yet beneath that peaceful appearance lies a world of constant motion, unimaginable energy, and endless vibration. If Earth is a place filled with sound, then the sun is something even more remarkable. It is a giant natural instrument, continuously producing waves, oscillations, and rhythms on a scale far beyond human experience. The sun contains more than 99% of all the mass in our solar system. It is so large that more than 1 million Earths could fit inside it. Deep within its core, nuclear fusion converts hydrogen into helium every second, releasing enormous amounts of energy. This energy begins a slow journey outward through layers of intensely hot plasma. The process is not smooth or quiet. Instead, the sun behaves like a vast ocean of boiling material, with currents rising, sinking, colliding, and mixing throughout its interior. Imagine heating a pot of water on a stove. As the water warms, bubbles form and currents begin to circulate. Hot material rises while cooler material sinks. The sun operates according to similar principles, but on a scale so immense that comparison almost loses its meaning. Great rivers of plasma move throughout the star. Massive cells larger than entire countries constantly churn across its surface. Every movement creates pressure. Every pressure change creates waves, and every wave contributes to a complex pattern of vibrations that fills the entire star. Scientists have discovered that the sun oscillates continuously. Its surface rises and falls in countless locations at the same time. Some regions move upward while others sink downward. These motions may only involve distances of a few kilometers, which sounds impressive until one remembers the sun itself is nearly 1.5 million kilometers wide. The movements are subtle relative to the star's size, yet they reveal a hidden world of activity taking place beneath the visible surface. These oscillations behave much like sound waves. Pressure disturbances travel through the sun's interior, bouncing between different layers and interacting with one another. The star effectively rings with thousands of different frequencies simultaneously. In some ways, it resembles a gigantic bell. In others, it resembles an enormous musical instrument playing many notes at once. The difference is that these notes are not heard with human ears. They exist as pressure waves moving through plasma rather than air. Researchers study these vibrations through a field called helioseismology. The name may sound complicated, but the basic idea is surprisingly simple. Just as geologists use earthquake waves to learn about Earth's interior, astronomers use solar vibrations to investigate what lies beneath the sun's visible surface. By observing how waves travel through the star, scientists can infer details about temperature, density, internal motion, and structure. The sun becomes a puzzle whose hidden pieces reveal themselves through vibration. When these solar oscillations are converted into frequencies humans can hear, the results are fascinating. The original vibrations occur at pitches far below the range of human hearing. However, by increasing their frequency while preserving their relationships, scientists can create audio representations. The resulting sounds often resemble deep humming, resonant tones, or slowly shifting musical chords. They feel strangely alive, as though the star itself is singing across the emptiness of space. The sun's vibrations are not limited to its interior. Its atmosphere is also a dynamic and restless environment. Powerful magnetic fields twist through layers of hot plasma, storing enormous amounts of energy. Occasionally, these magnetic fields become tangled and unstable. When they suddenly reorganize, they release bursts of energy known as solar flares. These eruptions can accelerate charged particles to tremendous speeds and send waves rippling across the solar atmosphere. The resulting disturbances are among the most energetic events in our solar system. Some solar eruptions launch gigantic clouds of plasma into space. These events, called coronal mass ejections, can contain billions of tons of material. As they expand outward, they interact with the solar wind and magnetic fields throughout the solar system. If one of these clouds reaches Earth, it can trigger spectacular auroras, while also affecting satellites, communication systems, and electrical infrastructure. Even though we cannot hear these events directly, they represent enormous releases of energy capable of producing powerful waves throughout the solar environment. One of the most remarkable facts about the Sun is that its vibrations never truly stop. Day and night, year after year, century after century, pressure waves continue moving through its interior. Long before humans appeared on Earth, the Sun was already oscillating. Long after our civilization is gone, those vibrations will continue. The star exists in a constant state of motion, balancing gravity pulling inward against energy pushing outward. That balance creates rhythms that have persisted for billions of years. From our perspective on Earth, sunlight feels steady and reliable. Yet hidden beneath that familiar glow lies a world of ceaseless activity. Vast currents flow through the interior. Magnetic fields twist and reconnect. Pressure waves race through layers of plasma. The entire star resonates with countless frequencies, forming a complex symphony far beyond ordinary perception. If we could somehow stand at a safe distance and hear the Sun directly through an atmosphere capable of carrying its vibrations, the experience would likely be overwhelming beyond imagination. As we continue our search for the loudest things in the universe, the Sun serves as an important reminder that even familiar objects can possess hidden dimensions. What appears calm from afar may be filled with motion. What seems silent may be vibrating continuously. The star that warms our planet every day is not merely a source of light. It is a giant cosmic instrument, endlessly performing a composition that began billions of years ago and continues even now, filling the solar system with invisible rhythms carried through plasma, magnetic fields, and energy itself. If someone could travel from planet to planet across our solar system, one of the first surprises would be how different each world feels. Earth is familiar, filled with wind, oceans, forests, storms, and an atmosphere that constantly carries sound. But beyond Earth lies a collection of worlds that seem almost silent. Mercury circles the Sun with barely any atmosphere at all. Mars possesses only a thin veil of air. The giant planets are wrapped in deep layers of gas and powerful magnetic fields. At first glance, it might seem that most of these places have little to contribute to a discussion about sound. Yet the more scientists study the planets, the more they discover that each world possesses its own hidden voice. The key to understanding these planetary voices is realizing that sound is not always what humans naturally hear. Throughout the universe, countless vibrations exist beyond the narrow range detectable by our ears. Some occur at frequencies far too low to hear. Others occur as electromagnetic waves rather than ordinary pressure waves. With the help of scientific instruments, researchers can transform these invisible signals into audio forms, allowing us to experience aspects of the solar system that would otherwise remain hidden. Among all the planets, Jupiter is perhaps the most famous example. Jupiter is not only the largest planet in the solar system, it also possesses an extraordinarily powerful magnetic field. This magnetic field stretches millions of kilometers into space and captures huge numbers of charged particles. As these particles move through Jupiter's magnetic environment, they generate radio emissions. These emissions are not sounds in the traditional sense. They travel as electromagnetic waves rather than vibrations through air. However, when scientists convert them into audible frequencies, the result is astonishing. The recordings often sound eerie and otherworldly. Sharp whistles rise and fall unexpectedly. Strange, crackling noises appear and disappear. Deep pulses emerge from the background like distant machinery operating in darkness. Listening to these transformed signals creates the impression of standing inside an alien environment. Although the sounds are scientific translations rather than direct recordings, they represent real physical activity occurring around the giant planet. Saturn possesses its own unique magnetic voice. For many years, spacecraft studying Saturn detected unusual radio emissions originating from the planet's magnetic environment. When converted into sound, these emissions produced haunting tones that seemed almost musical. Some listeners described them as resembling distant songs, while others compared them to electronic instruments or mysterious broadcasts from another civilization. The reality is less dramatic, but no less fascinating. The sounds arise from interactions between magnetic fields, charged particles, and the complex environment surrounding the planet. Even smaller planets contribute to this hidden orchestra. Mars, despite its thin atmosphere, offers valuable clues about how sound behaves on another world. When robotic explorers arrived on the Martian surface carrying microphones, they provided humanity with the first opportunity to listen directly to sounds on another planet. The recordings revealed a surprisingly unfamiliar environment. Winds moved differently through the thin atmosphere. Vibrations traveled in unusual ways. Sounds seemed softer and more distant than equivalent noises on Earth. Even simple gusts of wind felt strangely alien, because the Martian atmosphere is so much less dense than our own. Venus presents an entirely different case. Beneath its thick blanket of clouds lies an atmosphere far denser than Earth's. Surface pressures are so extreme that conditions resemble being deep beneath an ocean. If a microphone could survive the crushing heat and pressure, sounds would travel very efficiently through the dense air. A thunderstorm on Venus could potentially produce powerful acoustic waves moving through an atmosphere, unlike anything humans have ever experienced naturally. The giant planets offer perhaps the most intriguing possibilities. Jupiter, Saturn, Uranus, and Neptune are not solid worlds in the same way Earth is. They contain enormous layers of gas and fluid-like material extending deep into their interiors. Powerful storms rage within these atmospheres. Winds can reach astonishing speeds. Massive weather systems persist for years, decades, or even centuries. These dynamic environments likely generate enormous pressure waves and complex vibrations that remain only partially understood. One reason planetary magnetic fields are so important is that they act like giant invisible structures interacting with the constant stream of charged particles flowing outward from the sun. This flow, known as the solar wind, continuously impacts planetary magnetic environments. The interactions create waves, disturbances, and oscillations that scientific instruments can detect. In some cases, these signals resemble whistles, pulses, or rhythmic patterns when converted into sound. The planets seem to communicate through a language written in magnetism and energy rather than air and vibration. Earth itself possesses a magnetic voice. Our planet's magnetic field protects us from much of the solar wind, guiding charged particles toward the polar regions where they help create auroras. These interactions also generate electromagnetic activity that can be measured and formed into audio. The resulting sounds often resemble soft whistles, crackles, or shifting tones. Even our own world participates in this hidden cosmic concert. What makes these planetary voices so fascinating is that they reveal activity occurring beyond ordinary perception. To human senses, the planets appear as distant points of light or beautiful spheres hanging in space. Yet behind those appearances lies constant motion. Magnetic fields twist and flex. Charged particles stream through invisible pathways. Atmospheres circulate around entire worlds. Storms grow, evolve, and dissipate. Every planet possesses its own unique character, expressed through patterns of energy that scientific instruments allow us to explore. As humanity continues sending spacecraft deeper into the solar system, we gain access to increasingly detailed recordings of these hidden environments. Each mission uncovers new layers of complexity. Worlds that once seemed silent reveal themselves to be rich with activity. Their voices do not resemble human speech, music, or familiar environmental sounds. Instead, they reflect the fundamental processes shaping entire planets. The search for the loudest thing in the universe often leads people to imagine giant explosions or catastrophic events. Yet before we reach those extreme phenomena, it is worth appreciating the quieter members of the cosmic orchestra. The planets demonstrate that even seemingly peaceful worlds can possess hidden voices. Beneath clouds, within atmospheres, and throughout magnetic fields, vibrations and signals travel continuously. The solar system is not silent. It is filled with whispers, hums, pulses, and tones, waiting for instruments capable of hearing them. When people think about thunderstorms, they usually imagine dark clouds gathering over familiar landscapes on Earth. A flash of lightning cuts across the sky, followed by the distant roll of thunder. It is one of the most powerful natural experiences available on our planet. Yet Earth may not have the most dramatic thunderstorms in the solar system. Beyond our world are planets where storms can grow to sizes that make entire continents seem small. Jupiter is perhaps the most impressive example. This giant planet is covered by deep layers of clouds and turbulent atmospheric bands. Within these enormous cloud systems, lightning storms occur that can release far more energy than typical thunderstorms on Earth. Spacecraft observations have revealed brilliant flashes illuminating the upper atmosphere. Some of these storms are thought to extend across regions larger than many countries. If a person could somehow float safely within Jupiter's atmosphere, the experience would likely be overwhelming. Massive clouds would tower above and below, while lightning illuminated an endless landscape of swirling gas. Saturn also experiences powerful electrical storms. In fact, some Saturnian storms have lasted for months at a time. These storms can grow so large that they wrap around significant portions of the planet. Instruments aboard spacecraft have detected radio emissions produced by lightning, providing evidence of intense electrical activity hidden beneath the clouds. Although we cannot directly hear these storms, the signals reveal an atmosphere constantly reshaped by powerful weather systems. Even worlds much farther from the sun appear capable of generating extraordinary storms. Neptune, despite receiving only a fraction of the sunlight that Earth receives, contains some of the fastest winds in the solar system. Giant weather systems move through its atmosphere at incredible speeds. Scientists continue studying how such distant planets maintain so much atmospheric energy despite their cold environments. Thunder itself requires an atmosphere. When lightning rapidly heats the surrounding gas, the air expands violently, creating a shock wave. On Earth, we hear that shock wave as thunder. On other planets, the exact sound would depend on atmospheric composition, density, temperature, and pressure. A thunderclap on another world might sound deeper, sharper, slower, or far stranger than anything familiar to human ears. What makes alien thunderstorms especially fascinating is their scale. On Earth, storms are local events. They may affect a city, a region, or sometimes an entire country. On giant planets, storms can persist for years and occupy areas larger than Earth itself. These weather systems remind us that nature operates on vastly different scales throughout the universe. As we continue our journey toward the loudest phenomena in existence, the storms of distant planets provide an important lesson. The universe does not need exploding stars or colliding black holes to produce powerful activity. Even ordinary weather, given enough size and energy, can become something extraordinary. Across the solar system, clouds gather, lightning flashes, and unseen thunder rolls through alien skies, creating atmospheric symphonies that have been playing for billions of years. The giant planets of our solar system are unlike anything found on Earth. Jupiter, Saturn, Uranus, and Neptune are not worlds with solid surfaces, mountains, forests, or oceans where a traveler could stand and look toward the horizon. Instead, they are vast spheres of gas and fluid-like material, wrapped in immense atmospheres that extend thousands of kilometers into space. These planets are so large that the weather systems inside them operate on scales almost impossible to imagine. On Earth, the atmosphere is relatively thin compared to the size of the planet. Most weather occurs within a narrow layer close to the surface. On the gas giants, however, the atmosphere is the planet. Winds, clouds, storms, and pressure systems stretch through enormous depths. The result is an environment where vibrations and waves can travel through immense volumes of gas. Jupiter provides one of the most dramatic examples. Its atmosphere contains powerful jet streams moving in opposite directions, creating the colorful bands visible through telescopes. Between these bands, turbulence constantly stirs the clouds. Some winds exceed speeds of hundreds of kilometers per hour. Deep below the visible cloud tops, pressures increase steadily, creating layers that scientists are still trying to understand. If human ears could survive in such an environment, they might hear a continuous background roar generated by moving gases, shifting pressure systems, and gigantic storms. The most famous feature on Jupiter is the Great Red Spot, a storm that has been raging for centuries. This enormous vortex is larger than Earth itself and rotates continuously through the planet's atmosphere. It is difficult to imagine what such a storm would sound like from nearby. The movement of vast masses of gas, combined with powerful winds and turbulent flows, could create a deep and relentless rumble, unlike anything experienced on our world. Saturn offers a different, but equally fascinating environment. Although its atmosphere appears calmer from a distance, it contains powerful storms and complex wind systems. The planet's clouds form beautiful patterns, while hidden below them, enormous atmospheric currents continue their slow circulation. Every layer contributes to a constantly changing system of pressure, waves, and motion. Farther from the Sun, Uranus and Neptune reveal that extreme weather is not limited to warmer worlds. Neptune, in particular, possesses some of the fastest winds ever observed in the solar system. Despite its great distance from the Sun, atmospheric currents can reach astonishing speeds. These winds race through the upper atmosphere, shaping clouds and generating dynamic weather patterns in a region where sunlight is incredibly faint. What makes gas giants especially important in our search for cosmic loudness is their ability to support enormous atmospheric waves. Just as oceans on Earth experience tides and swells, giant planets can host waves that travel through vast regions of gas. Some may take days or weeks to complete their motion. Others may persist for years. These planetary vibrations are often invisible, yet they reveal the immense energy stored within these worlds. The deeper scientists study the gas giants, the more they realize that these planets are not quiet spheres drifting through space. They are active, restless systems filled with motion. Winds circle entire worlds. Storms grow and fade. Pressure waves move through layers of gas thousands of kilometers thick. While they may not produce the loudest phenomena in the universe, they demonstrate that even planets can generate forms of atmospheric activity on scales far beyond anything found on Earth. As the giant planets continue their slow journeys around the Sun, their vast atmospheres remain in constant motion. Hidden beneath colorful clouds are powerful currents and endless waves, creating deep planetary rhythms that have persisted for billions of years. These worlds remind us that sound, vibration, and motion are not rare exceptions in the cosmos. They are woven into the very structure of the universe itself. Far beyond the planets of our solar system, beyond the familiar glow of the Sun, there exist objects so strange that they seem almost impossible. Among the most remarkable are pulsars, dense stellar remnants that spin through space with extraordinary precision. While they do not produce sound in the ordinary sense, their rhythmic signals have earned them a reputation as some of the most fascinating natural timekeepers in the universe. A pulsar begins its life as a massive star. For millions of years, the star shines by fusing elements in its core, releasing enormous amounts of energy. Eventually, however, the fuel runs low. Gravity begins to win the struggle against the outward pressure generated by fusion. The star collapses and explodes in a supernova, one of the most powerful events in the cosmos. What remains can be an incredibly dense object known as a neutron star. These neutron stars are astonishing. A sphere only a few dozen kilometers wide can contain more mass than the sun. The material is packed so tightly that a small amount would weigh billions of tons on Earth. During the collapse, the star's rotation speeds up dramatically, much like a figure skater spinning faster when pulling their arms inward. The result is an object rotating at incredible speed. Some pulsars spin once every few seconds. Others rotate dozens or even hundreds of times each second. As they spin, powerful beams of energy shoot outward from their magnetic poles. If one of these beams sweeps across Earth, astronomers detect a pulse of radiation. This pulse repeats every time the star completes a rotation. To observers, the effect resembles a cosmic lighthouse. The remarkable thing is the precision. Many pulsars keep time so accurately that they rival some of the best clocks ever created by humans. Their pulses arrive with astonishing regularity, continuing year after year with barely any variation. In a universe often associated with chaos and violence, pulsars provide a surprising example of stability. When scientists convert pulsar signals into audible frequencies, they create sounds that resemble steady beats, clicks, or drum-like rhythms. Some are slow and deliberate. Others are rapid and almost mechanical. Listening to them can feel like hearing the heartbeat of a distant machine hidden among the stars. The faster pulsars are especially impressive. Known as millisecond pulsars, they can rotate hundreds of times every second. Imagine an object more massive than the sun spinning faster than a kitchen blender. The forces involved are almost beyond comprehension. Yet these extraordinary remnants continue their rotations for millions, or even billions of years. Pulsars also influence their surroundings. Their intense magnetic fields accelerate charged particles to tremendous speeds, creating energetic environments filled with radiation. In some cases, streams of particles flow outward into space, carrying energy far beyond the star itself. These interactions generate additional waves and signals that astronomers can study. For our search for the loudest things in the universe, pulsars represent an important step. They are not the most energetic objects we will encounter, but they demonstrate how extreme conditions can produce powerful and remarkably organized patterns. Unlike storms or atmospheric turbulence, pulsars generate rhythms of extraordinary precision. They are less like roaring explosions and more like giant cosmic drums, beating steadily across the darkness of space. As countless stars shine quietly throughout the galaxy, scattered among them are these compact remnants of ancient explosions. They spin endlessly, sending pulses across the cosmos with unwavering regularity. Invisible to the naked eye, they create rhythms that travel through space for thousands of light years. In the vast cosmic orchestra, pulsars provide the beat, steady, reliable, and endlessly fascinating. If pulsars are the steady drummers of the universe, magnetars are the wild and unpredictable percussion crashes. They belong to the same family as neutron stars, born from the deaths of massive stars. Yet they possess a characteristic so extreme that they stand apart from nearly every other object known to science. They contain the strongest magnetic fields ever discovered in the universe. To appreciate how extraordinary this is, consider a simple refrigerator magnet. It can hold a note against a metal surface using a relatively weak magnetic field. Earth's magnetic field guides compasses, and helps protect the planet from charged particles arriving from space. The magnetic field of the sun is powerful enough to create solar storms that affect entire planets. A magnetar, however, exists on a completely different level. Its magnetic field can be trillions of times stronger than Earth's. These magnetic fields are so intense that they can influence matter in ways rarely encountered elsewhere in nature. If a magnetar were somehow placed much closer to Earth, its magnetic field could disrupt electronic devices from enormous distances. Fortunately, the known magnetars are safely scattered throughout the galaxy, far away from our planet. Despite their small size, usually only around 20 kilometers across, magnetars contain more mass than the sun. Their interiors are packed with matter compressed to astonishing densities. At the same time, their magnetic fields twist and strain the star's crust. Over time, these stresses build up. Eventually, the crust can crack or shift suddenly, releasing enormous amounts of energy. When this happens, the magnetar produces a burst. These bursts are among the most powerful events observed in our galaxy. In a matter of seconds, a magnetar can release more energy than the sun emits in months or even years. Space telescopes detect intense flashes of high-energy radiation spreading across vast distances. Even from tens of thousands of light-years away, these eruptions can be measured clearly by instruments orbiting Earth. Scientists sometimes compare these events to stellar earthquakes. Just as tectonic stress builds within Earth's crust before an earthquake occurs, magnetic stress accumulates within a magnetar before being released suddenly. The resulting disturbance sends waves through the star itself, causing it to vibrate. In an interesting way, these vibrations resemble ringing. After major eruptions, astronomers have detected oscillations moving through magnetars. The star effectively shakes, much like a bell after being struck. These vibrations provide valuable clues about the structure and properties of the dense matter hidden inside. Although the frequencies are not directly audible to humans, they can be converted into sound for study and presentation. The resulting audio representations often feel dramatic and mysterious. Deep tones, pulses, and resonances emerge from data collected across enormous distances. They offer a glimpse into environments so extreme that ordinary experience provides almost no comparison. What makes magnetars especially important in our search for cosmic loudness is the sheer amount of energy involved. Their eruptions are not merely local disturbances. They are galaxy-scale events capable of sending detectable signals across thousands of light-years. If a magnetar burst occurred within a dense atmosphere capable of carrying sound efficiently, the resulting noise would likely be beyond anything a human mind could imagine. Yet, despite their violence, magnetars are relatively rare. Only a small number have been identified within our galaxy. Their extreme magnetic fields eventually weaken over time, causing them to become less active. For a brief period in cosmic history, however, they stand among the most powerful objects in existence. As they drift through the Milky Way, these magnetic monsters remain hidden from casual observation. They do not shine brightly like ordinary stars. Instead, they wait in darkness, storing tremendous magnetic energy until another eruption occurs. When it does, the event briefly reminds the universe that even small objects can unleash astonishing power. Among the countless worlds, stars, and nebulae scattered across space, magnetars occupy a special place. They show that loudness in the cosmos is not always connected to size. Sometimes a relatively small object can produce effects that echo across an entire galaxy. Their bursts, vibrations, and magnetic storms bring us another step closer to understanding the most energetic and powerful phenomena the universe has to offer. Throughout most of a star's life, it appears stable and dependable. For millions or even billions of years, it shines steadily, producing light and heat while gravity and nuclear fusion remain in balance. Yet for some massive stars, this peaceful existence eventually comes to a dramatic end. When the final moments arrive, the result is one of the most powerful explosions in the universe. A supernova. A supernova marks the death of a massive star, but it is also the beginning of something new. In just a few seconds, a star that may have existed for millions of years releases an enormous amount of energy. For a short time, a single exploding star can shine brighter than an entire galaxy containing billions of stars. The scale of the event is difficult to imagine because nothing similar exists in everyday human experience. As the star runs out of fuel, its core can no longer support the immense weight pressing inward. Gravity suddenly gains the upper hand. The core collapses at incredible speed, compressing matter into an extraordinarily dense state. Then, almost instantly, the collapse triggers a violent rebound. A powerful shockwave races outward through the star, tearing it apart from within. The outer layers are blasted into space at millions of kilometers per hour. If a supernova occurred close enough and inside an atmosphere capable of transmitting sound, the resulting noise would likely be unimaginable. The explosion releases more energy in a few moments than the sun will produce during its entire lifetime. Of course, real supernovae occur in the near vacuum of space, so no traditional sound wave can travel across the vast distances between stars. Nevertheless, the event creates enormous pressure waves within the star itself before the explosion breaks free. In a sense, the star experiences its own final roar. Astronomers studying supernovae often focus on the shock wave produced during the explosion. This shock wave moves outward through stellar material, carrying tremendous energy. Even after the star has been destroyed, the expanding debris continues pushing into surrounding gas and dust. Over thousands of years, the shock wave can create vast structures known as supernova remnants. Some of these remnants remain visible long after the original explosion has faded. Beautiful filaments of glowing gas stretch across space, marking the location where a star once existed. Although they appear calm in photographs, these structures are still expanding. The shock waves continue moving through the surrounding environment, transferring energy and shaping nearby regions of space. Supernovae are also responsible for creating many of the elements that make life possible. The iron in your blood, the calcium in your bones, and countless other elements were forged inside ancient stars before being scattered across the galaxy by explosions like these. Every atom heavier than hydrogen and helium has a story connected to stellar evolution and cosmic violence. In this way, supernovae are both destructive and creative. They destroy stars while enriching the galaxy with the raw materials needed for future stars, planets, and living things. The death of one generation helps make the next generation possible. Scientists sometimes convert data from supernova observations into sound audio. These sonifications allow researchers and the public to experience patterns hidden within the data. The resulting audio often contains rising tones, deep pulses, and dramatic changes in intensity. While these are translations rather than direct recordings, they help illustrate the immense energy involved in these cosmic events. For our search for the loudest thing in the universe, supernovae are among the strongest candidates we have encountered so far. They release staggering amounts of energy and generate powerful shock waves capable of reshaping entire regions of space. Yet surprisingly, even more extreme phenomena still await us. As the debris from ancient supernovae drifts through the galaxy, it carries the memory of stars that once shone brightly in the darkness. Their final explosions continue expanding long after the original event has passed, spreading energy and matter across interstellar space. In the grand cosmic symphony, a supernova is not a gentle note or a steady rhythm. It is a tremendous crash of soundless thunder, powerful enough to echo through the structure of a galaxy itself. When a supernova explodes, the event itself lasts only a short time. The brilliant flash fades. The star disappears. and from a distance, it may seem as though the story is over. In reality, the explosion is only the beginning of a much longer chapter. The energy released during a supernova continues traveling outward for thousands, and sometimes tens of thousands, of years. Long after the star has vanished, its shockwave keeps moving through space, carrying the memory of the explosion across enormous distances. A shockwave is different from an ordinary wave. It forms when energy is released so suddenly and violently that the surrounding material cannot move out of the way smoothly. Instead, a sharp front develops, compressing everything in its path. On Earth, shock waves can be produced by lightning, explosions, or supersonic aircraft. In space, supernova shock waves operate on scales so vast that comparison becomes difficult. As the expanding wave moves outward, it collides with clouds of gas and dust scattered throughout the galaxy. These clouds may have remained relatively calm for millions of years before the shockwave arrives. Suddenly, they are compressed, heated, and reshaped. Entire regions of space can be transformed by the passing disturbance. The remnants left behind by supernovae are among the most beautiful structures ever observed. Vast glowing filaments stretch across light years of space, forming intricate patterns that resemble cosmic webs. Through telescopes, they appear delicate and peaceful, yet these structures are actually evidence of tremendous violence. They exist because powerful shock waves continue pushing outward, interacting with the surrounding environment. One famous example is the Crab Nebula. This object was created by a stellar explosion observed from Earth nearly 1,000 years ago. Today, the remnant continues expanding into space. The original star is gone, but the energy from its death still influences the region around it. As shockwaves travel through interstellar gas, they can generate turbulence and complex motions. Material becomes stirred and mixed. Magnetic fields are compressed and twisted. Charged particles are accelerated to extraordinary speeds. Some of these particles eventually become part of the cosmic rays that move throughout the galaxy. In a way, the shockwave acts like a messenger. It carries information about the original explosion into regions far beyond the star itself. Every cloud it encounters is affected. Every particle it accelerates becomes part of a larger story that began with a dying star. These expanding waves also play an important role in creating future generations of stars. When shock waves compress large clouds of gas, they can trigger gravitational collapse. Regions that were once stable begin to contract. Over time, new stars may form within these compressed areas. The death of one star can help initiate the birth of many others. This cycle has repeated throughout the history of the galaxy. Stars form, shine, and eventually die. Their explosions send shockwaves across space. Those shockwaves help create new stars, which will one day repeat the process. The Milky Way is not a static collection of objects. It is a constantly evolving environment shaped by these recurring waves of energy. If human ears could somehow hear a supernova shockwave moving through dense material, the sound would likely be unlike anything imaginable. It would not be a brief bang or a sudden crash. Instead, it would resemble an immense and sustained roar, spreading across distances measured in light years. The energy involved is simply too great for ordinary comparison. Even after thousands of years, many supernova remnants remain active. Their shock waves continue expanding, though more slowly than before. They gradually lose energy as they interact with surrounding material, but their influence can persist for astonishing lengths of time. As we move deeper into our exploration of the loudest phenomena in the universe, these expanding shock waves reveal an important lesson. Loudness is not always about a single dramatic moment. Sometimes the true impact of an event lies in what happens afterward. A supernova may last only a short time, but its shockwave can continue shaping the galaxy for ages. Long after the original explosion has faded into history, the echoes of that cosmic catastrophe remain alive, moving silently through the darkness, carrying energy from a dead star into the future. Few objects in the universe capture the imagination as strongly as black holes. They are often portrayed as cosmic vacuum cleaners, endlessly pulling everything around them into darkness. While that image is somewhat exaggerated, black holes are among the most extreme objects known to exist. They possess gravity so powerful that once something crosses a certain boundary, known as the event horizon, it cannot escape. Not even light can return. At first glance, black holes may seem completely silent. After all, they emit no light of their own and are surrounded by the vacuum of space. Yet the regions around black holes are often among the most energetic environments in the universe. Far from being quiet voids, they can generate enormous amounts of activity, creating phenomena that indirectly produce some of the most powerful signals astronomers have ever observed. Many black holes are surrounded by disks of gas and dust. This material does not immediately fall inward. Instead, it spirals around the black hole at tremendous speeds, forming what is known as an accretion disk. As particles within the disk collide and rub against one another, they become extremely hot. Temperatures can rise to millions of degrees, causing the disk to shine brightly across multiple wavelengths of light. The process is surprisingly chaotic. Vast amounts of matter race around the black hole, while magnetic fields twist and stretch through the disk. Turbulence develops. Shock waves form. Energy is released continuously. If these environments could somehow be translated into ordinary sound, they would likely resemble an immense and constant roar. Some black holes also launch gigantic jets of particles from regions near their poles. These jets can travel for thousands or even millions of light years, carrying enormous amounts of energy far beyond the black hole itself. Although scientists are still studying exactly how these structures form, they represent some of the largest and most powerful features in the known universe. Perhaps the most fascinating aspect of black holes is what happens when they interact with one another. In some regions of space, two black holes become gravitationally bound and begin orbiting a common center. Over time, they spiral closer together. As they do, they disturb the very fabric of space and time. For centuries, this idea would have sounded like science fiction. Today, it is one of the most important discoveries in modern astronomy. When black holes orbit one another, they generate ripples known as gravitational waves. These waves travel outward across the universe at the speed of light. Unlike ordinary sound waves, gravitational waves do not require air, water, or any other material medium. Instead, they are distortions in space itself. As the black holes move closer, the waves become stronger and more frequent. The system effectively produces a rising signal, often compared to a chirp when converted into sound. Then comes the final merger. The two black holes collide and become one larger black hole. In a fraction of a second, enormous amounts of energy are released as gravitational waves. The resulting signal may last only moments, yet it can carry more power than all the stars in the observable universe combined during that brief period. When scientists first detected gravitational waves directly, it marked one of the greatest achievements in the history of astronomy. For the first time, humanity had observed the universe through an entirely new form of information. The signal came from two black holes that had merged more than 1 billion years earlier. Their collision had sent ripples across the cosmos, and those ripples eventually reached Earth. Researchers often convert these detections into audio. The famous sound is surprisingly simple. It begins at a lower pitch, rises rapidly, and ends abruptly. The recording lasts less than a second. Yet hidden within that brief chirp is the story of two black holes spiraling together and releasing unimaginable energy. Black holes remind us that loudness in the universe is not always connected to noise. Some of the most powerful events do not produce sounds that ears could hear directly. Instead, they create waves, vibrations, and disturbances that reveal themselves through careful observation and advanced technology. As we continue our journey, black holes stand as powerful contenders in the search for the loudest things in existence. Their mergers shake space itself. Their surroundings blaze with energy. Their influence extends across enormous distances. Yet even among these cosmic giants, there are still phenomena capable of producing disturbances on even larger scales. Deep within the darkness between the stars, black holes continue their silent work. Matter falls inward. Jets stream outward. Space bends around them. Occasionally, two of these invisible giants meet and merge, sending ripples across the universe that travel for billions of years. To human ears, the cosmos may seem quiet, but hidden beneath that silence are echoes powerful enough to reshape our understanding of reality itself. As we search for the loudest thing in the universe, one particular discovery appears again and again. It is often described as the deepest sound ever detected in the cosmos, a note so low that no human being could ever hear it naturally. This remarkable signal comes from a place known as the Perseus Galaxy Cluster, one of the largest known structures in the nearby universe. Galaxy clusters are enormous collections of galaxies bound together by gravity. Instead of containing just a few stars or a single galaxy, they contain hundreds or even thousands of galaxies spread across millions of light years. Between these galaxies lies a vast amount of extremely hot gas. Although this gas is incredibly thin compared to Earth's atmosphere, there is so much of it that it fills much of the cluster. At the center of the Perseus cluster sits a giant galaxy known as ENGI 1275. Hidden within this galaxy is a supermassive black hole containing hundreds of millions of times the mass of the Sun. This black hole is not quietly sitting in darkness. It is actively interacting with the surrounding gas, injecting enormous amounts of energy into the cluster. Over time, astronomers noticed something unusual. Observations revealed giant cavities within the hot gas surrounding the central galaxy. These cavities appeared as though something had blown enormous bubbles into the cluster. The source turned out to be the supermassive black hole itself. As matter fell inward, energy was released, pushing material outward and creating expanding structures within the gas. These expanding bubbles generated pressure waves. Because the cluster contains gas, pressure waves can travel through it, just as sound waves travel through air. The process is extremely slow because of the enormous scales involved. A single wave may take millions of years to complete one cycle. Nevertheless, from a physical perspective, these waves are very similar to sound. When scientists analyzed the data, they discovered a remarkable fact. The dominant frequency of the waves corresponded to an incredibly low musical note. The pitch was approximately 57 octaves below middle C. Human hearing cannot come remotely close to detecting such a frequency. Even the deepest sounds produced by musical instruments are enormously higher. To put this into perspective, if a piano could somehow continue extending downward octave after octave, it would still be nowhere near the frequency observed in the Perseus cluster. The note is so deep that one complete vibration takes an extraordinarily long time. It exists far beyond the limits of ordinary sound. Despite being inaudible, the discovery captured public imagination. For the first time, astronomers had identified something that could reasonably be described as a sound moving through a structure millions of light years across. The idea that an entire galaxy cluster could resonate with a low-frequency note felt almost poetic. Scientists later converted the data into audible form by raising the frequency enormously. The resulting audio does not represent what human ears would hear naturally, but it allows us to experience the pattern hidden within the measurements. The transformed sound resembles a deep, haunting tone, emerging from the darkness of space. What makes this discovery especially important is its scale. Earlier in our journey, we explored sounds associated with planets, stars, pulsars, and supernovae. The Perseus cluster operates on an entirely different level. Here, the medium carrying the waves stretches across millions of light years. The source of the disturbance is a supermassive black hole. The resulting pressure waves influence enormous regions of intergalactic space. In some ways, This is one of the closest examples we have to a true cosmic sound. Unlike electromagnetic signals that are converted into audio for convenience, these are actual pressure waves moving through matter. The matter is extremely thin, and the frequencies are unimaginably low, but the underlying physics remains familiar. The discovery also revealed something important about galaxy clusters. Without a source of energy, the hot gas within clusters would gradually cool. Yet many clusters remain hotter than expected. The pressure waves generated by central black holes help distribute energy throughout the surrounding gas, preventing it from cooling too quickly. In other words, these enormous cosmic vibrations play a role in regulating the evolution of entire galaxy clusters. As night covers our small world, the Perseus cluster continues its slow resonance hundreds of millions of light years away. Galaxies drift through the cluster. Hot gas fills the spaces between them. At the center, a supermassive black hole continues shaping its environment. The pressure waves it generates move outward at a pace almost impossible to imagine, carrying the deepest known note through one of the largest structures in the universe. It is a sound no ear could ever hear directly, yet it remains one of the most extraordinary examples of cosmic vibration ever discovered. A reminder that even the largest structures in existence can possess their own hidden rhythms. The Perseus cluster is not unique in possessing enormous waves moving through hot intergalactic gas. As astronomers studied other galaxy clusters, they began discovering that many of these vast structures are far more active than they once appeared. From a distance, galaxy clusters can seem calm and motionless, like islands of light scattered across the darkness. In reality, they are dynamic environments where gravity, hot gas, magnetic fields, and supermassive black holes constantly interact. A galaxy cluster is among the largest structures held together by gravity. Some contain hundreds of galaxies, while others contain thousands. Yet the galaxies themselves are only part of the story. Between them exists a huge reservoir of extremely hot gas. This gas can reach temperatures of tens of millions of degrees, making it hotter than the surface of many stars. Although it is incredibly thin, the sheer volume of material is enormous. Because this gas fills such vast regions, it can support waves on scales almost impossible to imagine. When energy is released near the center of a cluster, often by a supermassive black hole, pressure disturbances spread outward through the surrounding material. These waves behave somewhat like ripples spreading across a pond, except the pond may be millions of light years across. The timescales involved are equally astonishing. On Earth, a sound wave may reach your ear in a fraction of a second. In a galaxy cluster, a wave can take millions of years to travel from one region to another. Entire species could evolve and disappear while a single disturbance slowly moves through intergalactic gas. Despite their slow nature, these waves carry tremendous energy. As they travel, they distribute heat throughout the cluster. This process helps prevent gas from cooling too rapidly and collapsing toward the center. In effect, giant pressure waves help regulate some of the largest structures in the universe. Astronomers have observed enormous cavities, shock fronts, and ripple-like patterns in several galaxy clusters. These features provide evidence that energy is continuously being injected into the surrounding gas. Supermassive black holes act almost like cosmic engines, releasing bursts of energy that keep entire clusters active over vast periods of time. One of the most surprising discoveries is that black holes can influence regions far larger than the galaxies that contain them. A supermassive black hole may occupy a relatively small area compared to a galaxy cluster, yet its energy output can shape structures extending across hundreds of thousands of light years. The resulting waves become part of the cluster's long-term evolution. If human hearing could somehow be expanded to detect frequencies far below its normal limits, and if a listener could survive within such an environment, galaxy clusters might seem filled with extraordinarily deep and slow vibrations. These would not resemble music in any familiar sense. Instead, they would be immense resonances unfolding over millions of years, more like the breathing of a cosmic giant than a conventional sound. The existence of these waves changes how we think about the universe. It is easy to imagine space as empty and inactive, especially on the largest scales. Yet observations reveal constant motion. Gas circulates, energy spreads outward, gravity reshapes structures over time. Even regions spanning millions of light years are not truly still. As we move closer to the most powerful phenomena in existence, galaxy clusters offer an important lesson. Loudness in the universe is not only about sudden explosions. Sometimes it is about scale. A pressure wave crossing a galaxy cluster may be extraordinarily slow, yet it influences volumes of space so vast that the human mind struggles to picture them. Far beyond the Milky Way, giant clusters continue their gradual evolution. Galaxies orbit through immense clouds of hot gas. Supermassive black holes release energy into their surroundings. Waves spread outward through intergalactic space. The process unfolds so slowly that it appears almost frozen from a human perspective, yet it never truly stops, hidden beneath the apparent stillness of the cosmos. These giant structures continue resonating with some of the deepest and largest vibrations ever discovered. When we picture galaxies, they often seem permanent and unchanging. Beautiful spirals shine quietly in the darkness, separated by enormous distances and drifting peacefully through space. Yet over long periods of time, galaxies are anything but still. Gravity continuously pulls them toward one another, and occasionally entire galaxies collide in some of the largest interactions in the universe. The word collision can be misleading because galaxies are mostly empty space. Even during a galactic merger, individual stars rarely crash directly into each other. The distances between stars are simply too great. Instead, the real drama occurs on a much larger scale. Vast clouds of gas interact, gravitational forces reshape entire structures, and billions of stars have their orbits altered. A galactic collision is not a brief event. It unfolds over hundreds of millions or even billions of years. During this time, the galaxies gradually distort each other. Their elegant spiral arms stretch outward. Long streams of stars form enormous tidal tails that can extend across hundreds of thousands of light years. The original shapes slowly disappear as gravity rearranges everything. If human ears could somehow hear the forces involved, the process would not resemble a crash or explosion. Instead, it might feel like a deep and continuous rumble lasting longer than human civilization has existed. The energies are immense, but they are spread across extraordinary distances and timescales. One of the most important consequences of galaxy collisions is the compression of gas clouds. As clouds interact and merge, they can trigger intense periods of star formation. Entire regions suddenly begin producing new stars at rates far higher than normal. Astronomers call these regions starburst galaxies because they appear to be experiencing a rapid burst of stellar birth. Within these star-forming regions, massive young stars quickly emerge. Many will eventually explode as supernovae, releasing even more energy into their surroundings. In this way, a galactic collision can indirectly create countless future explosions throughout the merging system. At the centers of many galaxies reside supermassive black holes. When galaxies merge, these giant black holes may eventually move toward one another. Over vast periods of time, they can form binary systems and gradually spiral together. The final stages of this process generate powerful gravitational waves, carrying enormous amounts of energy across the universe. Long before the black holes merge, however, their surroundings become extremely active. Gas falling toward the galactic centers can heat to extraordinary temperatures. Jets may form, radiation increases. Entire regions become some of the brightest locations in the cosmos. Astronomers have observed many examples of galaxies in various stages of collision. Some appear connected by glowing bridges of stars. Others display long arcs and distorted shapes created by gravitational interactions. These systems provide a glimpse into the future of our own galaxy. The Milky Way is currently moving toward the Andromeda Galaxy. Although there is no cause for concern, the two galaxies are expected to begin merging billions of years from now. By then, Earth and humanity will almost certainly be long gone. But the event serves as a reminder that galactic collisions are a natural part of cosmic evolution. What makes these mergers fascinating in our search for cosmic loudness is that they create enormous amounts of activity without producing a single dramatic moment. Unlike a supernova, which explodes in seconds, a galaxy collision unfolds gradually. The noise of the event comes from countless smaller processes occurring simultaneously. Gas clouds collide, stars form, black holes feed, gravitational fields shift. The entire system becomes a complex network of interacting energies. From a human perspective, the universe often appears quiet because its largest events happen so slowly. Yet if we could speed up time and watch billions of years pass in moments, colliding galaxies would reveal themselves as remarkably dynamic places. Streams of stars would stretch across space. Clouds would compress and ignite. Bright regions would flare into existence before fading once more. As we continue our journey toward the loudest phenomena in the cosmos, galaxy collisions remind us that power does not always announce itself with sudden violence. Sometimes it unfolds gradually, reshaping entire regions of the universe over unimaginable spans of time. Beneath the calm appearance of the night sky, galaxies are constantly moving, interacting, and transforming, creating a vast and invisible symphony that has been playing since the earliest ages of cosmic history. Among all the objects discovered in the universe, few are as astonishing as quasars. For a time, astronomers did not even understand what they were. Through telescopes, they appeared as tiny points of light, almost like ordinary stars. Yet, something about them seemed wrong. They were located at enormous distances, far beyond our galaxy. And despite that distance, they shone with incredible brightness. Eventually, scientists realized they were looking at some of the most energetic objects ever observed. A quasar is powered by a supermassive black hole located at the center of a galaxy. Unlike the relatively quiet black hole at the center of the Milky Way today, the black holes that create quasars are actively feeding on huge amounts of surrounding material. Gas, dust, and even entire stars can be pulled toward the black hole's gravitational grip. Before this material disappears beyond the event horizon, it forms a rapidly spinning accretion disk. Within that disk, conditions become extreme. Matter races around the black hole at tremendous speeds. Friction and collisions heat the material to extraordinary temperatures. The disk begins releasing enormous amounts of radiation, often outshining every star in the host galaxy combined. This is what makes quasars so remarkable. A region smaller than a galaxy can produce more light than hundreds of billions of stars. If such an object were located where a normal star sits in the night sky, it would dominate the heavens. Fortunately, quasars are generally found billions of light years away. Even at those immense distances, they remain visible to our instruments because of their extraordinary power. In terms of cosmic loudness, quasars represent a different kind of intensity. They are not single explosions like supernovae. Instead, they are sustained engines operating continuously for millions of years. The amount of energy released over that time is almost beyond comprehension. Around a quasar, vast quantities of gas are accelerated outward. Powerful winds sweep through the host galaxy. Some quasars produce gigantic jets that extend far beyond the galaxy itself, carrying energy across intergalactic space. These jets can stretch for hundreds of thousands of light years, becoming some of the largest structures associated with a single object. If the environment around a quasar could somehow transmit ordinary sound efficiently, The result might resemble a continuous cosmic roar. Material is constantly falling inward, colliding, heating, and being accelerated outward. The energy involved dwarfs nearly anything found within a normal galaxy. What makes quasars especially fascinating is that they were far more common in the early universe. Billions of years ago, galaxies contained larger supplies of gas, giving supermassive black holes abundant fuel. During that era, the cosmos was filled with bright quasars shining across vast distances. The young universe was a much more energetic and active place than the one we see around us today. As astronomers look deeper into space, they are also looking farther back in time. Some quasars are so distant that their light began its journey when the universe was only a small fraction of its current age. They provide valuable clues about how galaxies and black holes evolved during the earliest chapters of cosmic history. Perhaps the most surprising aspect of quasars is how such enormous power originates from gravity itself. The black hole is not generating energy like a star through nuclear fusion. Instead, energy comes from matter falling inward. As material descends into one of the deepest gravitational wells in the universe, tremendous amounts of energy are released before the material disappears forever. This process transforms the black hole's surroundings into one of the brightest environments known to science. As we continue our search for the loudest thing in the universe, quasars stand among the strongest contenders. Their energy output can exceed that of entire galaxies. Their jets cross intergalactic distances. Their influence can shape the evolution of the galaxies that host them. Far beyond the Milky Way, countless quasars once illuminated the darkness of the young cosmos. Though many have faded over billions of years, their ancient light continues traveling through space. Even now, some of those photons are arriving at Earth, carrying the message from an era when supermassive black holes blazed like cosmic lighthouses, creating some of the most powerful and energetic environments the universe has ever known. As powerful as quasars are, some of their most remarkable features are the enormous jets they produce. These jets rank among the largest structures created by a single object in the universe. They begin near supermassive black holes, yet they can extend for hundreds of thousands, and sometimes even millions, of light years into space. To appreciate their scale, imagine a beam that starts near a black hole and stretches far beyond the boundaries of an entire galaxy. Scientists are still working to understand every detail of how these jets form, but the general picture is becoming clearer. Near a supermassive black hole, matter spirals inward through a rapidly rotating disk. Powerful magnetic fields thread through this chaotic environment. Under the right conditions, some of the material does not fall into the black hole. Instead, it becomes trapped within magnetic structures and is launched outward at enormous speeds. The resulting jets are incredibly narrow compared to their length. They remain focused across distances so vast that they seem almost impossible. Even after traveling for hundreds of thousands of light years, many jets retain their overall structure. It is as though a cosmic laser has been projected across intergalactic space. The particles within these jets often move at speeds close to the speed of light. As they travel, they interact with surrounding gas and magnetic fields. These interactions generate radiation across many wavelengths, allowing astronomers to observe the jets from great distances. In some cases, bright lobes form at the ends of the jets where the outgoing material collides with intergalactic gas. If we could somehow hear the energy flowing through one of these structures, it would likely resemble a continuous and overwhelming torrent. The amount of power being transported is extraordinary. Entire galaxies can be affected by the energy carried outward through these beams. One of the most important discoveries of modern astronomy is that black holes do not simply consume matter. Through jets and other processes, they can also influence vast regions far beyond their immediate surroundings. A supermassive black hole occupying a relatively small area can affect gas, stars, and even galaxy evolution across enormous distances. The largest jets known are so immense that light itself requires millions of years to travel from one end to the other. Human minds naturally struggle with such scales because nothing in everyday life offers a useful comparison. Mountains, oceans, and even planets seem tiny when measured against structures of this size. These jets also help distribute energy throughout the universe. Without them, some galaxies might evolve very differently. By heating surrounding gas and preventing excessive cooling, jets can influence where stars form and how galaxies grow. They are not merely spectacular features. They are active participants in the story of cosmic evolution. What makes them relevant to our search for cosmic loudness is the sheer amount of energy involved. While they do not produce ordinary sound, they represent sustained flows of power operating across distances almost beyond imagination. Their influence extends far beyond the black holes that create them. As astronomers observe these giant structures, they are witnessing energy released near one of the most extreme environments in nature and transported across intergalactic space. The process can continue for millions of years, creating enormous cosmic landmarks visible across vast distances. Far from the quiet image many people associate with space, these jets reveal a universe filled with motion and activity. Matter streams outward. Magnetic fields guide colossal flows of particles. Energy spreads through regions larger than entire galaxies. Hidden within the darkness are structures so vast that they reshape their surroundings over millions of years. In the growing orchestra of cosmic phenomena, these jets are not brief notes or sudden crashes. They are more like sustained blasts from an unimaginably powerful instrument, carrying energy across the universe and reminding us that some of the loudest things in existence do not announce themselves through sound, but through the immense and continuous movement of matter and power across the cosmos. So far, our journey has explored stars, planets, black holes, galaxy clusters, and enormous jets of energy. Many of these phenomena involve vibrations, pressure waves, or processes that can be compared to sound. But now we arrive at something even stranger. Gravitational waves are not sound waves at all. They do not travel through air, water, gas, or plasma. Instead, they travel through space itself. For centuries, space was often imagined as a silent stage upon which the events of the universe unfolded. Modern physics revealed a much more surprising reality. Space is not merely empty nothingness. It has structure. Massive objects can bend it, stretch it, and influence its geometry. Gravity is not simply a force pulling objects together. It is also a consequence of how matter and energy shape the fabric of the universe. When extremely massive objects move, they can create ripples in that fabric. The effect is similar to dropping a stone into a calm pond. Waves spread outward from the disturbance. In the case of gravitational waves, however, the waves move through space and time themselves. They travel outward at the speed of light, carrying information about the event that created them. Most gravitational waves are incredibly weak by the time they reach Earth. Even powerful events occurring across the universe produce distortions so small that detecting them requires instruments of extraordinary sensitivity. For decades, scientists knew gravitational waves should exist, but measuring them seemed almost impossible. That changed in the 21st century. Researchers built detectors capable of measuring changes thousands of times smaller than the width of a proton. When a gravitational wave passes through Earth, it stretches space in one direction and compresses it in another. The effect is tiny, yet detectable with sufficiently advanced technology. The first direct detection came from two black holes spiraling together more than 1 billion light-years away. For millions of years, they orbited each other, gradually losing energy through gravitational waves. As they moved closer, they orbited faster and faster. Finally, they collided and merged into a single larger black hole. The energy released during that final moment was astonishing. For a brief fraction of a second, The collision produced more power than all the stars in the observable universe combined. Most of that energy was emitted as gravitational waves. The resulting ripple traveled across space for over 1 billion years before reaching Earth. Scientists converted the signal into sound so people could experience it more easily. The famous result is often called a chirp. Taite. It begins at a lower frequency, rises rapidly, and ends suddenly. The entire recording lasts less than a second. Despite its simplicity, that short chirp represents one of the most important scientific discoveries in history. For the first time, humanity had directly detected ripples in space itself. Since then, many additional gravitational wave events have been observed. Some involve black holes. Others involve neutron stars, the incredibly dense remnants of exploded stars. Each detection provides new information about some of the most extreme environments in existence. What makes gravitational waves especially fascinating is that they allow us to observe phenomena that might otherwise remain hidden. Light can be blocked, scattered, or absorbed. Gravitational waves pass through most matter almost unaffected. They carry information directly from the heart of violent cosmic events. In terms of loudness, gravitational waves challenge the very meaning of the word. They are not sounds, yet they originate from some of the most energetic events in the universe. They represent disturbances on a scale so fundamental that they affect the structure of reality itself. As we move closer to the ultimate answer to our question about the loudest thing in the universe, gravitational waves reveal that cosmic power can take forms far stranger than ordinary sound. Sometimes the greatest disturbances do not shake air or gas. Sometimes they shake space itself. Across the cosmos, black holes continue merging. Neutron stars continue colliding. Massive objects continue sending ripples outward in every direction. Most will travel for millions or billions of years before reaching distant observers. Invisible and silent to human senses, these waves move endlessly through the universe, carrying the echoes of ancient collisions and reminding us that even space itself is capable of vibrating. When we search for the loudest thing in the universe, we eventually reach a point where individual objects no longer matter. Stars, black holes, and galaxies all exist within something even larger, the history of the universe itself. At the beginning of that history lies an event so extreme that it defines everything that came after it: the Big Bang. The Big Bang was not an explosion in space. It was the expansion of space itself. In its earliest moments, the universe was unimaginably hot and dense, far beyond anything that exists today. Matter and energy were not yet organized into atoms, stars, or galaxies. Everything was compressed into a rapidly expanding state where temperatures and energies reached levels we can only describe through mathematics and theory. In those first moments, the universe was filled with a dense, energetic plasma. Particles moved freely, constantly interacting with radiation. Under these conditions, pressure waves could travel through the cosmic medium. These waves were not sound in the everyday sense, but they behaved in a similar way. Regions of slightly higher density created compression. That compression spread outward, forming enormous oscillations across the young universe. In a very real sense, the early universe was filled with a kind of cosmic sound. These primordial oscillations were incredibly large in scale. Some waves stretched across regions that would later become entire galaxy clusters. Others influenced how matter would eventually clump together to form the first stars and galaxies. The structure of the universe today still carries the imprint of these early vibrations. Modern cosmology has found evidence of these ancient patterns in the faint radiation that fills all of space. This radiation, known as the cosmic microwave background, is a remnant of the early universe when it first became transparent to light. Embedded within it are tiny variations in temperature and density. These variations are the fossilized echoes of those early pressure waves. If we could somehow listen to the early universe, it would not sound like anything familiar. There would be no sharp noises or distinct events. Instead, it would be a continuous, evolving hum, shaped by the constant interplay of energy and matter. The frequencies involved would be far too low for human hearing, and the timescales far too long to perceive directly. Yet, mathematically, the structure resembles something very close to a universal resonance. As the universe expanded, these waves gradually stretched and slowed. The hot plasma cooled, and atoms began to form. Light was finally able to travel freely through space. The era of primordial sound slowly faded away. What remained was a universe filled with subtle patterns, waiting for gravity to shape them into stars and galaxies. In this way, the loudest moment in cosmic history is also the quietest. It contained more energy and more motion than any other period, yet it occurred in a medium so different from air or water that traditional sound cannot properly describe it. Still, the idea of a cosmic beginning filled with vibration remains one of the most powerful concepts in modern science. Everything we observe today, from galaxies to black holes to planetary systems, can ultimately trace its origin back to those early fluctuations. The universe did not begin as a collection of isolated objects. It began as a single dynamic system, filled with waves of energy and density that would later shape everything we know. As the cosmos continues to expand, those ancient patterns remain written into its structure. Even now, billions of years later, astronomers can still detect their influence across vast distances. The echoes of the beginning have never truly disappeared. They have simply stretched across time and space, becoming part of the universe's ongoing evolution.